American billionaire Elon Musk promises to send a human to Mars as early as the year 2029, and in the second half of the 21st century, according to Musk's plan, a full-fledged colony with a population of 1 million people is supposed to appear on Mars. Optimists and space exploration enthusiasts hope that the founder of SpaceX will succeed in implementing his plan, although there are plenty of skeptics who doubt that anything like that can be achieved using the technologies currently available to SpaceX. In today's video, we will talk about how we could possibly get to Mars, what is required for this, how exactly the Martian expeditions are planned to be organized at SpaceX, what problems they may encounter in the process of organizing such missions, and what solutions are being considered today. And before we begin, I would like to kindly ask my dear viewers to support the work of our project by becoming a sponsor, right here on YouTube or on our Patreon and Boosty pages. All necessary links will also be in the video description. Huge thanks to everyone who is already supporting the project, helping me make it better and better, and also to those who decide to join our list of sponsors today. Well then, make yourselves comfortable, because our virtual Martian expedition is about to begin. Let us begin, of course, with the theory of the matter. In one of our previous videos, in which we explored the mechanics of space flights, I already said that all bodies in space move along certain orbits around specific gravitating centers. The Moon revolves around the Earth itself and other planets, around the Sun, around the center of our galaxy, and so on. The same applies to artificial spacecraft. At every moment in time, they also move along some orbit, and any space journey essentially represents a sequence of changes in the orbits along which such a spacecraft travels. This means that our ability to make a space journey depends on whether we can switch between the required orbits. The orbit that a spacecraft is on at any given moment is determined by its speed at a given point in space. Therefore, in space travel, distance is not that important. What matters is the ability to change the spacecraft's velocity so that it ends up on the required orbit. Because once it is on that orbit, it will definitely reach its destination without any additional effort. That is why the key concept in the theory of spaceflight is the so-called delta V budget. That is, the amount by which a spacecraft can change its speed using the fuel reserves on board. This refers, of course, to the total speed change during the entire flight. For example, if our spacecraft needs to accelerate by 3 kilometers per second and then decelerate by 2 kilometers per second, the total delta V budget will be 5 kilometers per second. Speed can be changed in space only through reactive thrust, meaning by firing rocket engines, and each such firing requires a certain amount of fuel, the supply of which cannot be replenished in space. That is why the delta V budget is directly linked to how much fuel is available on board the spacecraft and how efficiently it uses that fuel. Let us see what orbital transfers need to be made to fly to Mars and what delta V budget we must have for that purpose. In fact, the only scenario currently available for a flight to Mars is the so-called Hohmann transfer. We also discussed this type of maneuver in more detail in the video where we looked at types of space maneuvers. At the initial moment, the spacecraft is on a low Earth orbit at a height of about 200 kilometers above the Earth's surface, where it has a velocity of approximately 7.5 kilometers per second. At a precisely calculated moment in time, the spacecraft fires its engines in order to transfer from a circular geocentric orbit to an elliptical heliocentric one, with the perihelion, that is, the closest point, located on Earth's orbit, and the aphelion on the orbit of Mars. Naturally, we need to aim not at where Mars is at the moment of engine ignition, but where it will be when the spacecraft reaches the perihelion of the orbit. In other words, the initial positions of the spacecraft, the Sun, Earth, and Mars relative to each other, must be roughly like this. Since Earth and Mars revolve around the Sun at different speeds, Earth completes one orbit in 365 days, Mars in 687, such an alignment happens roughly every 780 days, or every 26 months, or once in 2 years and 2 months. In other words, a Mars expedition along a Hohmann trajectory can be launched only about once every 2 years. One such launch window was missed in October 2024, and the next will open in November or December 2026. That is exactly when SpaceX has scheduled its first test unmanned Mars mission. There are other orbits that can lead to Mars, but they either require a larger delta-V budget or take longer to travel. So for now, the Hohmann transfer remains the only realistic option. To leave low Earth orbit and head for a Hohmann trajectory toward Mars, the spacecraft needs to increase its velocity by approximately 4 kilometers per second. This is the first component of our delta-V budget, which our ship must have at its disposal, based on its fuel reserves and engine capabilities. After completing this maneuver, the spacecraft will travel most of the way by inertia in the gravitational field of the Sun, and if everything is done perfectly correctly, there will be no need to fire the engines or burn fuel until reaching Mars. In reality, of course, doing everything with absolute precision is hardly possible, and along the way, the trajectory might need small adjustments, for which our delta-V budget should include something like 0.5 kilometers per second. After about 6 to 7 months of flight, the spacecraft will approach Mars, and now our task is to take it off the elliptical heliocentric orbit, because otherwise it will just keep moving along it and return to the perihelion, and not even to Earth, but to the place where Earth was at the moment of departure, which obviously is not what we want. To prevent that, we will need to reduce its speed from 5.5 kilometers per second, which is about how fast it will be moving relative to Mars, to 3.5 kilometers per second. This gives us one more contribution to our delta-V budget, approximately 2 kilometers per second. The next stage is landing on Mars, during which the spacecraft's speed relative to Mars needs to be reduced from the orbital 3.5 kilometers per second to 0, which adds another 3.5 kilometers per second to the delta-V budget. In reality, however, this value will be smaller. Mars does have an atmosphere, although it is thin, so it will help us reduce speed. Taking this into account, the actual delta-V budget for this final phase of the flight will be about 2.5 kilometers per second. Thus, a flight from low Earth orbit to Mars, including landing on the surface of the red planet, will require a delta-V budget of about 9 kilometers per second. It won't be possible to just walk around Mars, take a few selfies, maybe collect some samples, and fly back. We must remember that Earth and Mars occupy the right positions for a transfer only about once every 26 months. Considering that the flight from Earth to Mars took us about 7 to 8 months, we will have to wait on Mars for about 18 to 19 months, roughly a year and a half, until the next launch window opens. When that time comes, we will need to begin our journey back. First, we will have to launch from the surface of Mars and reach Martian orbit, which will require us to gain the same orbital velocity of 3.5 kilometers per second. However, now the Martian atmosphere will hinder us in doing this, so the actual delta-V budget will be closer to 4 kilometers per second. Then, we will need to enter the same kind of elliptical orbit we used to get from Earth to Mars, which will require accelerating the spacecraft by another 2 kilometers per second. And finally, when approaching Earth, we will need to leave this orbit and re-enter Earth orbit, requiring another reduction in velocity by around 4 kilometers per second. Thus, the total delta-V needed for the return journey from the Martian surface to Earth orbit is about 10 kilometers per second, and the total round trip will require about 18 to 19 kilometers per second. That is a huge amount. If we speak specifically about Starship, which SpaceX plans to use for the first expedition to Mars, then at the moment of reaching Earth orbit after launch, its tanks must still hold about 500 tons of propellant. To be more exact, propellant meaning both fuel and oxidizer. To calculate what speed Starship can reach with that amount of propellant, we use the Tsiolkovsky equation. In this formula, ISP is the specific impulse of the engine, meaning the ratio of thrust to fuel consumption per second, Capital M is the mass of the ship, including payload and fuel, and small m is the mass of fuel alone. For Starship, the specific impulse is 3,726 meters per second. The dry mass of the ship without fuel or payload is 120 tons, and the payload mass for the Mars mission, according to Elon Musk, is expected to be 100 tons. In the end, we find that after spending 500 tons of propellant, Starship can expect a delta V of approximately 4.4 kilometers per second. This will be just enough to reach the Hohmann transfer orbit leading from Earth to Mars, but not enough for the maneuver to enter Martian orbit or to land on Mars. And it is precisely such estimates that feed the skepticism of those who doubt that Musk's grand plans can be realized. SpaceX is aware of this problem too, but they insist they know how to get around it and still make the seemingly impossible interplanetary flight a reality. The first part of the clever plan is the idea to refuel Starship in low Earth orbit. That is, while the Martian Starship is circling the Earth, special Starship tanker vehicles are launched from Earth to space one after another, each of which, according to SpaceX estimates, can deliver up to 100 tons of propellant to the main mission ship, allowing its 1,200-ton tanks to be filled almost to capacity in about 6 to 8 trips. With 1,200 tons of fuel and 100 tons of payload, the 120-ton Starship can reach a speed of about 7 kilometers per second. However, this is still less than the required delta V of 9 to 10 kilometers per second needed for the flight to Mars and landing on its surface. So SpaceX engineers had to come up with something else. And they did. The solution is the idea to completely skip the phase of entering Mars orbit. Instead, Starship is to perform what's called a direct entry, descent and landing maneuver, making maximum use of the Martian atmosphere's resistance to reduce speed. According to the plan, at the final stage of the maneuver, Starship's trajectory will be adjusted to enter the Martian atmosphere directly at an altitude of about 50 to 70 kilometers and at an angle of 10 to 12 degrees. At such entry parameters, even the thin Martian atmosphere will exert significant resistance to the spacecraft's motion and will effectively reduce its speed in place of the engines. Once Starship descends to about 2 to 3 kilometers above the Martian surface, it will fire its engines and perform a controlled landing. Using the direct entry maneuver will reduce the delta V budget to about 5 to 6 kilometers per second, and this discount will allow Starship with 1,200 tons of fuel and 100 tons of payload to travel from Earth to Mars and perform a successful landing on the surface of the red planet, staying within the available delta V budget of 7 kilometers per second. Taking into account all maneuvers, about 250 tons of fuel will still remain in the tanks by the time of landing on Mars. Thus, in-orbit refueling and using direct atmospheric entry make a mission to Mars possible for Starship. However, if we are talking about a crewed mission, the astronauts still need to return to Earth, which, as we recall, requires a delta V budget of about 10 kilometers per second, even more than the journey to Mars. However, the delta V required for the flight back to Earth can be significantly reduced if we attempt the same trick with direct entry and landing, only this time with braking in Earth's atmosphere. This will save about 4 to 5 kilometers per second, reducing the total return delta V to about 5 to 6 kilometers per second. But even in that case, Starship's tanks must hold at least 400 to 500 tons of fuel, 1.5 to 2 times more than will be available after landing on Mars. There are 2 possible ways out of this deadlock. The first and simplest is to send not 1, but 2 ships to Mars, the main Starship and an unmanned tanker ship carrying an additional fuel supply. The tanker ship does not land on the planet's surface, but instead enters some orbit around Mars and waits for the main ship to launch from the surface. Calculations show that about 600 tons of fuel could remain aboard such a tanker by that time, which is enough for both ships, the crewed main Starship and the unmanned tanker, to successfully return to Earth. This plan looks perfectly viable, setting aside certain technical problems and questions, which we will discuss later in this same video. But Elon Musk wouldn't be Elon Musk if he didn't propose a much more impressive project. Let's recall that the travelers will have to spend about a year and a half on Mars anyway. So why not use that time to do something useful, such as producing fuel for the return trip? This idea, by the way, is far from new. The concept of setting up a small fuel plant on Mars for return missions has been discussed since the 1980s. At the heart of the idea is the so-called Sabatier reaction, in which 1 mole of carbon dioxide from the Martian atmosphere reacts with 4 moles of hydrogen to form 1 mole of methane and 2 moles of water. The water can later be split into hydrogen and oxygen through electrolysis. The hydrogen can be returned to the system and the oxygen used as an oxidizer for the methane. It won't be a completely closed cycle, of course, because the output gives us only half as much hydrogen as was originally input. But this is not a major issue, since the missing hydrogen can be obtained by electrolysis from water, which is abundant on Mars in the form of ice. In some regions of Mars, including Utopia Planitia, which is being considered as one of the possible landing areas for Starship, the ice content in the soil reaches up to 30% by mass. According to SpaceX estimates, Starship can be equipped with gear capable of producing about 100 tons of methane and 200 tons of oxygen per month. So in a year and a half, there will be enough fuel for the return journey. So in theory, Musk's plan for conquering Mars, even in its most ambitious form, appears quite realistic. But as always, the devil is in the details, and there are plenty of those details capable of derailing the entire mission at every stage of this plan. Even the spacecraft itself, Starship, cannot yet be called a proven technology. Out of 8 launches, 5 have ended in failure, including the latest as of this video's release, on the 6th of March 2025, when the ship exploded over the Caribbean Sea 10 minutes after launch. Of course, such failures are common during the testing of a new spacecraft, but it's far from certain that Starship will be ready by late 2026. The date set? We remind you, for the first unmanned Mars test mission. And if they fail to meet that deadline, then the whole program gets pushed back by at least another 2 years. There are also certain doubts regarding the idea of orbital refueling of Starship before the flight to Mars. This technology is not yet proven either. In any case, 8 tanker launches from Earth in a short period of time to refuel the mission's main ship is a demanding schedule even for SpaceX. The third issue is the long journey from Earth to Mars and back. This is not a problem for unmanned missions, but when we are talking about a ship carrying humans, not only the delta-V budget matters, but also the time spent in flight. At the very least, because the ship must carry supplies of food, water, and oxygen for the entire journey. For one person, a one-way trip will require about 218 kilograms of oxygen, 1.5 tons of water, and 500 kilograms of food, over 2 tons per person, or 20 tons for 10 people, which is the number planned for the first Mars mission according to SpaceX. Even if we use recycling systems for water and oxygen, similar to those used on the ISS, which significantly reduce consumption, we're still talking about at least 20 to 30 tons of cargo just to sustain a crew of 10 astronauts for the whole mission. That is about 1/3 of the total payload capacity of the ship, which significantly limits what else can be taken on board. Perhaps the key issue is the direct atmospheric entry maneuver that makes the Starship Mars mission possible in the first place. Deceleration due to atmospheric drag means intense heating due to friction, since the spacecraft's kinetic energy is essentially converted into heat, which places very high demands on the ship's thermal protection. Such a maneuver requires extremely precise calculation of entry parameters and strict adherence to them. If the entry angle is slightly too steep, the heating will be too intense and the ship will burn up. If the angle is too shallow, Starship will simply bounce off the Martian atmosphere like a stone skipping across the surface of water. In principle, the direct entry and landing maneuver has already been used in various Mars missions. It was how the rovers Pathfinder, Curiosity, and Perseverance were delivered to Mars. However, In the case of Starship, it will be the first time this maneuver is performed with such a large vehicle. It is not certain that Starship's design will be ready for such a test. In addition, we must not forget that after the direct entry maneuver, Starship will have to perform a controlled landing on an unprepared site. And this is something that no one has ever done before. This stage is perhaps the riskiest of all, and that is why SpaceX is approaching its development very seriously. Before a crewed ship lands on Mars, they plan to land as many as 5 uncrewed Starships in this same way. The success of those landings will to a large extent determine whether it is reasonable to count on a successful landing of the crewed ship. Many questions also relate to life support for the astronauts during their stay on Mars, as well as the operation of the fuel production plant itself. According to Musk's own statements, the plant will weigh around 20 tons, which fits comfortably within Starship's 100-ton payload capacity. The challenge may lie in its power supply. SpaceX currently considers solar panels as the main power source both for the plant and for the colony as a whole. But at the current stage of solar power technology, this option looks questionable. For example, just the methane and oxygen production facility alone would require about 2 megawatts of electrical power, and that's before factoring in the base's own electricity needs. Considering Martian conditions, generating that much power would require about 15,000 to 20,000 square meters of solar panels, weighing no less than 50 tons, more likely closer to 80 or 90 tons, which, along with other cargo, goes far beyond Starship's lift capacity. True, SpaceX proposes delivering part of the cargo, including those same solar panels, using the 5 uncrewed Starships intended to practice Mars landings. But even in that case, deploying solar arrays of that size in Mars's unfamiliar environment will be a major technical challenge, as will maintaining them under the heavy dust conditions of the Martian atmosphere. An alternative could be a compact nuclear system capable of providing the required power at a mass of only 20 to 30 tons or even less. Russia is developing a so-called megawatt-class nuclear power propulsion system, capable of producing up to 4 megawatts of thermal power and around 1 megawatt of electric power with a total mass of just 7 tons. There are similar developments in the United States, though their performance is somewhat less impressive. For instance, under NASA's Kilopower project, a unit is being developed that could theoretically provide around 3 megawatts of power at a mass starting from 30 tons. However, whether such systems will be ready to operate by the year 2029 remains unclear. In conclusion, it can be said that, in theory and principle, the plans of SpaceX and Elon Musk may seem fantastic, but they are not impossible, at least from the standpoint of orbital mechanics and current spaceflight capabilities in general, and those of SpaceX in particular. In other words, the chances that a human foot will step on Mars within the next decade look fairly good. Still, even if the project is entirely successful, Mars flights will remain a highly complex and costly technical endeavor for a long time, making Musk's plans for a full-fledged human colony on Mars seem rather unrealistic. To make such a vision a reality, we will likely need fundamentally new space technologies. For example, electric propulsion or nuclear-powered rocket engines, like the ones we discussed in one of our previous videos. We will definitely keep following the progress of SpaceX's Mars project, as well as other exciting ventures in space exploration. And I hope we will return to this topic more than once in our future videos. That's all for today. Take care, dear friends, and see you again very soon in our next videos.